In this topic we're going to be exploring the idea of a dynamic equilibrium in chemistry and how it determines the conditions under which reactions are carried out in industry in order to maximise the efficiency of product production. The starting point is to understand that some reactions are reversible. The reactants can form the products, but the products can also react together to form the reactants. The way we show this in a balanced chemical equation is by changing the arrow symbol in the reaction. A reaction which is not reversible, such as burning methane, has the normal forward arrow symbol, showing that water and carbon dioxide can't then react together to make methane and oxygen. When a reaction is reversible, we use a double-headed arrow. In this example, ammonium chloride can decompose to make ammonia and hydrogen chloride, but ammonia and hydrogen chloride can also react together to make ammonium chloride. If we look at this reaction in practice, we can take some white ammonium chloride crystals in a test tube and heat them. This causes the forward reaction to take place, and the solid ammonium chloride thermally decomposes to form ammonia gas and hydrogen chloride gas, which are both colourless. These gases travel up the test tube, and when they reach a cooler part of the test tube, the ammonia and hydrogen chloride react together and form white ammonium chloride again, which is deposited on the walls of the test tube. This reverse reaction is a neutralisation. Hydrogen chloride is acting as an acid and donating a hydrogen ion to ammonia, which is acting as a base and accepting the hydrogen ion to become an ammonium ion. We're therefore justified in writing this reaction using a double-headed arrow to show it as reversible. Another reaction that is useful because of its reversible nature is the use of copper sulphate as a test for water. Blue copper sulphate crystals are hydrated, containing 5 waters of crystallization. If we heat these crystals, they turn white as the water vapour is given off and the copper sulphate becomes anhydrous. The equation shows that hydrated copper sulphate can be heated to make it anhydrous, and because it's reversible, anhydrous copper sulphate will react with water to become hydrated again. This means that if we add water to anhydrous copper sulphate, it will turn blue as the crystals become hydrated, and this forms a useful test for the presence of water. In a very similar reaction, pink hydrated cobalt chloride crystals can be heated to drive off some of the water of crystallization. The crystals turn blue. Adding water to the blue cobalt chloride turns it pink again, so this also provides a practical test for the presence of water. One further idea we need to understand regarding reversible reactions. We know that reactions are either exothermic, giving out heat energy, or endothermic, taking in heat energy to turn into chemical energy. With a reversible reaction, it will be exothermic in one direction and endothermic in the opposite direction. The amount of energy released when the reaction goes in the exothermic direction will be exactly equal to the amount of energy taken in when the reaction goes in the endothermic direction. We have no way of knowing which direction will be exothermic and which will be endothermic just by looking at the reaction, so we will usually be told or given the information to work this out in the question. Under some circumstances, it is possible to have reactants reacting to form products at the same time as the products are reacting to form the reactants again. This means the reaction is going both directions simultaneously, so there will be a mixture of products and reactants present in the reaction mixture. You might like to think about this as being like trying to run up a moving staircase which is going downwards. If you run up at the same speed as the escalator is going down, you will stay in the same place. This is a dynamic equilibrium where the two rates are in balance. In chemistry, a dynamic equilibrium will be set up if the forward and backward reactions in a reversible reaction are happening at the same rate as each other. Just like our runner, there will be no observable change. The amounts of reactants and products in the mixture will be staying the same because every time reactants collide successfully and form products, there will also be products colliding successfully to form the reactants again. One further condition for a dynamic equilibrium is that we must have a closed system. In other words, we mustn't allow any of the reactants or products to escape from the reaction mixture. To help picture this, Imagine two reactants A and B which can react together reversibly to form products C and D. If we start our reaction by mixing A and B together, they will begin to react, and the rate of their reaction will slow down as A and B are used up and C and D are formed. The difference between reversible reactions and non-reversible reactions is that once some C and D has been formed, these can start to react together to make A and B again. Initially, there will be very little of C and D, so the rate of this reaction will be very slow. As more C and D is produced in the forward reaction, there will be more of it available to react, so the rate of C and D reacting will increase. Eventually, the rate of the forward reaction will have decreased and the rate of the reverse reaction will have increased to the point where the rates are the same. An equilibrium has been reached. If you're making notes, here is the explanation we've just covered. You can pause the video whilst you note these down. We can visualise a reaction establishing a dynamic equilibrium like the container here with two taps. The top tap represents the forward reaction, adding products to the reaction container. To start the reaction, we open the top tap and start turning reactants into products, and the container starts to fill. As it fills, we slowly close the top tap and open the bottom tap, representing the reverse reaction turning products back into reactants. If we continue closing the top tap and opening the bottom tap, we will reach a point at which the level in the container neither rises nor falls, because the flow in is happening at the same rate as the flow out. This is our dynamic equilibrium. One common misconception is to think that there is always an equal amount of the reactants and the products present at equilibrium. This is not the case. Think again about the container with two taps. We can set the two taps to let water in and out at the same rates, regardless of whether the container is almost empty, half full, or almost full. This is true of chemical equilibrium too. We can have an equilibrium where there are lots of the reactants and hardly any of the products, or an equilibrium where there are similar amounts of products and reactants, or an equilibrium where we have almost all products. In fact, we can affect the amounts of products and reactants present at equilibrium by changing the conditions for the reaction, such as the temperature or the pressure. When we change the conditions, and this results in changing the amount of reactants and products present in the reaction mixture, we call this changing the position of equilibrium. For example, if we change the conditions so the position of equilibrium moves in the forward direction, to the right, we will have more products and less reactants present at equilibrium. Conversely, if we change the conditions so that the position of equilibrium moves in the backward direction, to the left, then we will have more reactants and less products present at equilibrium. So we need to understand how the position of equilibrium will change when we make a change to the conditions, so that we can choose which conditions will give us the best position of equilibrium, usually to give us as high a yield of the products as possible. The principle that drives the position of equilibrium is that when we make a change to the conditions, the position of equilibrium shifts to minimise the effect of that change. For example, if we increase the temperature, the position of equilibrium will shift in whichever direction the reaction is endothermic, in order to take in the added heat energy and convert it into chemical energy. Of course, this does mean we have to know in which direction the reaction is endothermic and in which direction it is exothermic. It follows that if we run our reaction to lower temperature, the position of equilibrium will shift in whichever direction is exothermic, so that some of the lost heat energy is replaced by the exothermic reaction. The effect of changing the pressure only applies to reactions with gaseous reactants or products, and pressure only has an effect when there are different numbers of moles of gas on each side of the equation. Remember, the numbers in front that we use to balance the equation are numbers of moles, so we need to look at the numbers in front and the G state symbols to decide how many moles of gas we have on each side. If the pressure is increased, the position of equilibrium shifts in whichever direction has fewest moles of gas, so that there are less gas particles present and the pressure changed is minimised. Conversely, decreasing the pressure shifts the position of equilibrium in the direction that has more moles of gases. If there are the same number of moles of gas on each side of the equation, changing the pressure will not affect the position of equilibrium. Here's an example of a reaction which can form an equilibrium. In this case, the reaction is endothermic in the forward direction. Using what you now know about controlling the position of equilibrium, what conditions, high or low, of temperature and pressure should be used to get the best yield of hydrogen from doing this reaction? Pause the video and make your suggestions with a reason for each condition you choose. If we want to make more hydrogen, then we need to choose the conditions that will move the position of equilibrium to the right, that is in the forward direction. The forward direction is the endothermic direction, and to get the position of equilibrium to move in the endothermic direction, we need to choose a high temperature. The forward direction also has more moles of gas, 1 mole of CO2 and 3 moles of H2, which is 4 moles of gas, compared to 1 mole of CH3OH and 1 mole of H2O on the left, which is only 2 moles of gas. To get the position of equilibrium to move in the direction of more moles of gas, we need to choose a low pressure. So high temperature and low pressure would give us the best yield of hydrogen. Here's a little quiz to see what you've picked up about reactions and equilibrium. Pause the video and make a note of whether you think each statement is true or false. Firstly, not all chemical reactions are reversible, so this is false. Secondly, the law of mass conservation tells us that the mass never changes during a reaction. It only seems to change if substances are added from the air or escape into the air, which can't happen in a closed system, so false. One of the conditions for a chemical equilibrium is that we have to have a closed system, so this one is true. The nature of reversible reactions is that reactants can form the products and the products can form the reactants, so this is true also. The double-headed arrow tells us that a reaction is reversible, not that an equilibrium has been set up. It's perfectly possible to have a reversible reaction that's not at equilibrium. Once an equilibrium has been reached, it's true to say that the amount of products and reactants stay the same, but this does not mean that no more products are formed. The products are being formed, but they're reacting and turning back into reactants at the same rate as they're being formed. Finally, a chemical equilibrium is a dynamic equilibrium. The forward and backward reactions have not stopped, but both reactions are going at the same rate. Now that we know about chemical equilibria and how the conditions affect them, we can apply our understanding to reactions that are used in industry. Here the emphasis is on sustainability, which means being able to make the products cost effectively from renewable raw materials, minimising energy use and minimising waste products. By optimising the reaction conditions, we aim to make as much product as possible using the minimum amount of energy necessary. We therefore need to consider temperature, pressure, catalysts, and how we will remove the products from the reaction mixture. The Haber process is used in industry to produce ammonia. The raw materials for making ammonia are nitrogen from the air and hydrogen, which can be made from natural gas and steam, or as a waste product of the petrochemical cracking that we met in the organic chemistry topic. We also use an iron catalyst and do the reaction at a temperature of 450 degrees C and a pressure of 200 atmospheres, which is 200 times our normal atmospheric pressure. Ammonia is made in huge quantities because it is the starting material needed to make many products which are used in large amounts, such as fertilisers, dyes, pharmaceutical products and explosives. The process starts with the nitrogen and hydrogen raw materials. which are combined together at 450 degrees C and 200 atmospheres over an iron catalyst. This is where the nitrogen and hydrogen react to form ammonia, but the reaction is reversible and only about 15% of the reaction mixture is ammonia. The gas mixture from the reactor is then cooled down. Ammonia has a much higher boiling point than nitrogen and hydrogen, so as the mixture is cooled below ammonia's boiling point, it condenses and turns into a liquid, leaving the hydrogen and nitrogen as gases. The ammonia can be run off as a liquid and stored, and the unreacted nitrogen and hydrogen can be recycled back into the reactor to be given another chance to react. By removing the liquid ammonia and recirculating the nitrogen and hydrogen, we make efficient use of the reactants, not wasting any of them, or the energy that was put into making them. The conditions of 450 degrees C and 200 atmospheres allow us to make ammonia at an optimum rate and cost. The 450 degrees C temperature is neither particularly high nor particularly low. To understand why it is the best temperature, we have to look at the reversible reaction which forms ammonia. We should know that this reaction is exothermic in the forward direction. This means that a low temperature will move the position of equilibrium in the forward direction and give us the most ammonia in the reaction mixture. However, the rate of reaction is also affected by temperature, and if we use a low temperature, the reaction will be slow and take too long to make the ammonia economically. We choose a moderate temperature of 450 degrees C as a compromise. It is low enough that we get a reasonable amount of ammonia in the reaction mixture, and high enough that the ammonia is formed at a reasonable rate. In addition, we use the iron catalyst to speed up the reaction, enabling us to use a lower temperature than we would otherwise need to in order to get the rate of reaction we want. The lower temperature means less energy is used in heating the reactor, and in turn this has benefits with less use of fossil fuels and less carbon dioxide released into the atmosphere from burning the fuels, leading to less climate change. The 200 atmospheres pressure is also only a moderately high pressure and chosen as a compromise. If we look at the balanced equation, we have 4 moles of gaseous reactants and 2 moles of gaseous products, so a high pressure will move the position of equilibrium in the forward direction, giving us more ammonia in the reaction mixture. Using a high pressure has an additional benefit because it also increases the rate of reaction, as there are more gas particles per centimetre cubed, so more frequent successful collisions. However, using a very high pressure requires a lot of energy and increases the risk of leaks or explosions, so the ammonia production equipment costs more to make and run. Using 200 atmospheres pressure gives us the optimum benefit without the costs becoming too great. Another industrial process which depends on controlling an equilibrium reaction is the production of sulphuric acid in the contact process. The raw materials are sulphur, which is obtained from petrochemical refineries after it's been extracted from oil and gas as a waste product, and oxygen, which is obtained from the air. The reaction is carried out at 450 degrees C and a pressure of 2 atmospheres, using vanadium 5 oxide as a catalyst. The process is carried out in 3 stages. In the first stage, sulphur is burned in oxygen, oxidizing the sulphur to form sulphur dioxide. An alternative raw material which can be used in the first stage is any sulphide ore, such as the iron ore known as fool's gold. Roasting a sulphide ore in air causes sulphur dioxide to be formed, as well as a metal oxide, iron 3 oxide in the case of the iron ore. Once we've made sulphur dioxide, the second stage is to convert the sulphur dioxide into sulphur trioxide by reacting it with oxygen. This is a reversible reaction, and we need to select the reaction conditions for this stage to optimize the amount of sulphur trioxide in the reaction mixture. Finally, we convert the sulphur trioxide into sulphuric acid. This is done by dissolving the sulphur trioxide in concentrated sulphuric acid that has already been made to form a liquid called oleum. The oleum can then be reacted with water to convert it into more sulphuric acid and can be diluted until the sulphuric acid solution is of the required concentration for sale. Like ammonia, sulphuric acid is made in large quantities industrially, as it is an important raw material for making fertilisers, detergents and soaps, and pigments for paints. To understand why a moderate temperature of 450 degrees C is used for the contact process, we need to examine the equation for the reversible reaction, and we need to know that the reaction is exothermic in the forward direction. If we want to get more sulphur trioxide in the reaction mixture, we need to move the position of equilibrium in the forward direction, which is the exothermic direction, so we will need a low temperature to do this. A low temperature, however, means a slow rate of reaction, so a moderate temperature of 450 degrees C is chosen as a compromise. It is low enough to have a reasonable amount of sulphur trioxide in the reaction mixture, and high enough to produce the sulphur trioxide at a reasonable rate. In addition, the vanadium 5-oxide catalyst allows us to use a lower temperature than we would otherwise have needed to get the rate we want, with the benefit of using less energy for heating the reactor. If we consider the number of moles of gas on each side of the equation, we can see that there are 3 moles of gaseous reactants that produce 2 moles of sulphur trioxide product. This means that a high pressure will move the position of equilibrium in the forward direction, giving a better yield of sulphur trioxide in the reaction mixture. A high pressure will also increase the rate of reaction. In this reaction, the position of equilibrium lies so far to the right, even at atmospheric pressure, that almost all of the sulphur dioxide turns into sulphur trioxide, so the cost of going to higher pressure to get the last fraction of a percent of sulphur trioxide is not justified, and a low pressure of 2 atmospheres is used in practice.